Cool video thing. Waiting for the cool video thing. All right, check that out. Cool. Okay, so any feedback on Justin's talk? Does that go okay? Okay. Really smart guy, doing cool stuff. The OpenCL stuff they're doing is very interesting. We're having a lot of internal talks about sort of where things are going as far as OpenCL versus CUDA versus what Intel's going to be doing with their native stuff. So we're very concerned about these sort of things. But for AMD, they're very interested in OpenCL, and that's certainly the direction they're going to be going for their GPU computing stuff. So anyway, it's going to be a lot of fun to watch over the next few months and years, which is good. John Nichols is coming tomorrow. He is the director of architecture for NVIDIA, specifically for GPU computing. He's pretty much the main guy behind why CUDA does what they do from a hardware point of view. So really stoked that he's coming up. I imagine that'll probably be the most full talk that we have. So I'm not expecting there's going to be a lot of empty seats in here. But he's also said that he will allow us to tape it and broadcast it, which surprised me a little bit, but that shouldn't stop you from asking really tough questions. Okay, let's see. Most of you have sent me project ideas. I will be getting back to you in the next day or two or three about those. And just my comments, some of it's going to be like, dude, you really need to go look at this paper and this paper, but I do want to be able to get back to you. So if you haven't sent me over email what you're thinking about doing, please do that. And I want to get back to you quickly. And then next Tuesday, we'll be due your formal proposals. And so we talked about how that worked, but that's sort of your contract with me, what you're actually going to do. Okay, any other administrative stuff? Okay. So we did rasterization last time, or we started rasterization. What we talked about was that it's two different problems, and one of the problems is figuring out which pixel values you're covering. Okay, and so we talked about specifically traversal. So how do we tell if something's in a triangle or not, and then how do we visit all the possible places to make sure that we hit them all? And then the second part of rasterization is figuring out the parameters inside. So if we have red here and green here and blue here, what color do we color each of these guys? And so that's the process of parameter interpolation. So we've finished, so I have a very brief review, but we finished traversal algorithms and the insidedness tests. And so we're going to spend most of the day talking about how we figure out what the parameters are. So we learned about this particular algorithm, this bounding box kind of traversal, where we just draw a big box around our triangle and then visit every location in and test whether it's inside or out. Okay, so it's a very simple thing to be able to do. It's obviously not very efficient because you end up visiting a lot of places that you're never ever going to actually rasterize. Okay, we also talked about Crow's algorithm. We're going to be doing that one again today. This is what's traditionally the Scanline algorithm. That a Scanline is sort of, it's on one single line going from left to right, or right to left, or other ways to do it. But it is a one-dimensional construct, usually called a span. Okay? And so the Scanline algorithm is that you start on the bottom Scanline and you work your way up, or you start on the top and you work your way down. So this is nice because it deals with any convex polygons, so it's good. And it's fairly efficient because you only visit the pixel locations that are actually in the polygon. You're not going to visit a bunch of stuff that you're not going to end up being able to use. Okay, we also talked about this Barycentric formulation here. And that seemed kind of silly when we talked about it, but what we're saying is we're going to define the areas in this triangle. We're going to define three triangles here, defined by the three vertices of the triangle and then the point we care about. So we want to know if this point is inside or outside the triangle. The way we're going to do that is we're going to define the areas of the red, green, and blue triangles such that if all three of those areas are positive, then we're inside the triangle. If those areas are negative, if we take this point and move it outside and sort of flip this triangle over, we define that as being negative, and that if any of the areas are negative, then we are not inside the triangle. Okay, so we kind of decided, like, that's a little bit hokey, that's a lot of work to go through, but what I hope I'll show you today is that this is actually very useful in doing parameter interpolation. Okay? One of the nice things here is that you have to calculate A0 and A1 and A2. to be able to do this, okay, to get these fractions. And what did we previously calculate the area of the triangle to do? Okay?
Previously culling.
Culling. So in culling, we figured out what the area of the triangle was. And all we cared about there was the sign, okay, is the area facing us or away from us. Okay? But here we see if we actually calculate the value of that, then it comes in handy. Okay? Here it comes in handy for this particular expression. To get this fraction, okay, the fraction, each of these here, we have to have the area of the whole triangle. So we calculate that during culling, we're going to use it here. So there's a little bit of redundancy going on. And we also looked at how you actually calculated the area of one of these triangles, and we saw it really wasn't too big. It was just a cross product. Okay, so it was fairly simple to be able to do that. Okay. Now, one kind of traversal that we didn't talk about was this tiled traversal. So I want to make sure that I explain this because this is pretty much the way that modern GPUs do it. Okay? That they do it in a hierarchical approach. They divide the screen into big tiles, and how big they are depends on the implementation, and then they rasterize within each tile. So the way we're going to do this is we divide all the screen space into these big tiles, and we traverse one tile at a time for this triangle. So we're going to be able to look at this and say, all right, which tiles does it intersect? Okay, in this case, we're going to say it intersects 6 big tiles, and then we will rasterize within each tile separately. Okay, so it's sort of a two-level approach. Which tiles do I cover? And then does the tile overlap with the triangle? And then we'll traverse the pixels inside the triangle. So this ends up being nice for several reasons. We're going to cover these sort of things later lectures. So one is that by considering an entire tile at a time to do rasterization, that works very nicely with the texture cache. Okay. 2 is it allows culling to work better, and we're going to talk about this later on. Okay, because there are culling algorithms that work on a tile basis. And we deal with a lot of compression when we actually send color and depth information to the memory system. And so we'd like to be able to compress those. That's very important. And again, we'll cover this in a later lecture as well. Okay? So how big are the tiles? That would be actually a very interesting experiment to run to figure out how big the tiles are. Okay? This is if you saw any difference in rasterization between sort of medium-sized, like short squat triangles, like sort of squarish triangles, versus really wide triangles versus really tall triangles. It might be as a result of this sort of effect. That I would expect that a triangle that's sort of squarish would have a better rasterization performance than ones that are really long and skinny, because something squarish is probably going to cover fewer tiles than something of the same area that's really long and skinny. But that's something that your results might or might not have shown. Okay, so is this really any different? Okay, well, it's not really different than what we've done already. All right, we already know how to figure out which tiles overlap the triangle. Right, that's just traversal of tiles instead of traversal of pixels. We already know how to traverse pixels inside a tile. And one of the nice things is we can get a lot of parallelism here. Right, you can just have a pixel stamp that goes down and picks these out. Right, you can say, all right, we're just going to test all 16 of those at the same time. Okay, you could do that in parallel if you chose to. The thing that's a little bit different here is you have to test if the tile overlaps the triangle. Okay, so now instead of saying, does this point overlap the triangle, you have to do, does this rectangle or this square overlap the triangle? And you can do this with edge functions. It's just a little bit more complicated math. Okay, any questions on traversal? So sort of these points are all things we're going to see again. And this is what graphics hardware kind of already does. Okay, so where we're going now is we did pixel coverage. What we're going to look at now is parameter determination. How do we figure out what the parameters are inside? Okay, so it's pretty simple to describe what we're trying to do here. Out of the vertex program comes several interpolants. So a value that we keep per vertex. So what are things that could be interpolants? What are the things that we want to take out of the vertex program and then interpolate across the triangle? Texture coordinates, that's a great one, right? Texture coordinates, where we have a texture coordinate at each vertex here, and we need to figure out what the texture coordinates are at every fragment within the triangle. What else? Normals, okay? So if we're doing per fragment shade, or lighting, okay, which is very typical today in a modern game, we need normals. What else?
Color.
Color, okay, something very simple. Depth, Okay, something else very simple. You could have multiple colors. You could have multiple texture coordinates. You could have multiple normals. You could have a normal and a binormal and a tangent vector. Right? You get to pick what you put in there, but the point is that any modern game is probably going to have several things that you're going to want to interpolate. Okay, so the answer, that what we want to figure out in rasterization is, for each interpolant, so we're going to have several interpolants, okay, what is the value of that interpolant at every pixel location? So what we're going to say is we want linear interpolation. Okay, we want linear interpolation for this I function. Okay, meaning that it's going to vary linearly across this. We're not going to do any weird curve fitting or anything. We're going to think of this as a 3-point function here, and we're just going to do a single plane that's going to define that function. All right. So if this is at 0 feet and this is at 12 feet and that's at 300 feet, we're just going to have 3 points making a plane. It's going to make a plane there. Nice linear plane, and we're going to pick out the value at every pixel location. Okay, so the simplest possible interpolation that we could do. Now, what we care about here is how much is this going to cost to be able to do it? As we look at these algorithms, we're going to look at the setup cost, which is the cost per triangle to do this calculation. Right? So big triangle, small triangle, doesn't matter. There's going to be some cost that we're going to incur every triangle, and there's going to be some cost that we're going to incur every fragment. Right? So for really, really big triangles, we're going to want to minimize the per fragment cost, because that's going to be most of our cost. For really, really tiny triangles, we're going to want to minimize the setup cost, because that's going to be most of our cost. Right? So when we talk about a triangle setup stage, we're talking about this. When we're talking about rasterization and fragment shader cost, we're talking about this. Okay? And so different algorithms have different trade-offs here. And so when we talk about, do we want a programmable rasterizer versus a fixed function rasterizer? Well, a fixed function rasterizer builds that in hardware. If you have a programmable rasterizer like Larabee's going to have, then you can maybe vary these. If you know you're going to have a lot of big triangles coming down the pipe, maybe you're going to pick a different algorithm to rasterize than if you have a lot of really small ones. Okay, so here's the Scanline algorithm. So I'm just going to draw it and talk along with it. So we've got big triangle here. Okay, and here's what we're going to do to rasterize this. Writing on the board now. You should get both of these in at the same time. Great. Okay, so what we're going to say, the big picture here is that if we want to figure out what the value is at this point here, we're going to do that in sort of 2 steps. One is that we're going to rasterize, we're going to figure out what the interpolation is between two of the vertices, and we're going to do the same thing here, right? So if you have these two here, then you can figure out what this value is. If you have these two here, then you can figure out what this value is. And so first we're going to figure out these two values, okay? And then we're going to interpolate between those two values. So it's sort of a 2-step thing that's going on. Because it's linear interpolation, you can sort of compose these two things, okay? So that's the big picture of what we're going to do. So we know on this edge we're going to have x naught, y naught. And on this edge we're going to have x1, y1. Okay? And so the first thing we're going to do is we're going to calculate the slope here, dx dy. Okay? So actually, that's right here, dx dy. All right? And we will calculate also how much the interpolant changes every time we go up a step. Okay? So that's going to be di dy. Okay? Okay? So as we move up by 1y, how much does x change? Right? So if we move up one scan line here, how much does x change? Okay? And as we move up one scan line here, how much does I change? Okay? How much does the interpolant change? We need these derivatives to be able to do the algorithm that we're going to do. So this is a setup cost, right? This is something we do on every triangle, no matter how big or small the triangle is. Okay? For each of the 3 edges here, we're going to calculate these derivatives. Okay? So that's cool. So now what we're going to do is we're going to start at the bottom, y here. Okay? We're going to figure out what the starting x position is here. Okay? Where's the first place where we basically hit a pixel center? And then we're going to calculate the finishing x over here. Okay? And then we're going to have a span that goes between these two things. We also need to calculate I0, which is the initial value of the interpolant at the beginning of the span. Okay. Then we say, okay, we're going to start at a place where we have an integer x and an integer y, and we're going to rasterize the span that goes across here. Okay? So if we have a really big triangle here, then it's going to be a long span. We're going to figure out, okay, this is the first place we need to be. This is x0. And this is the last place we need to be, which is x1. And we will rasterize along this span. Okay. Now, the cool thing about this algorithm is that we have a starting point for the interpolant here. And then as we move to the next interpolant, we can calculate, if we know the interpolant value here at I0, and we want the interpolant value here at I sub x, we can do that incrementally, because we know the I dx. Okay? We know every time we take a step in x, how much the step is in terms of the interpolant. We can calculate that. All right? And so if the interpolant here is 12 and the I dx equals 2, then as we move along here, we just add. That's 14, that's 16, and so on. So it's just an incremental calculation as we walk across this scan line. So we've gone to all this effort here so that when we have a nice big triangle and we have a really long span, as we hop from pixel to pixel, all we have to do to get the next interpolant is just do an addition. Okay, so we do one addition on every fragment that we visit. Okay? So there's a cost associated with the setup of the entire triangle. There's a cost associated with the setup of every span, but then the cost per fragment ends up being pretty low. It's just one addition per interpolant for every fragment we do as we walk along this span. Okay. The other trick is that once we reach this point here and we switch from this edge to this edge, there's a little bit of bookkeeping that goes along. Okay. So this is the Scanline algorithm. This is historically how things have been done. All right? So it merges pixel coverage and parameter determination, and that's kind of cool, right? Because it uses Crow's algorithm to figure out which pixels we're going to cover, and it also calculates what the interpolants are as it's walking down that scan line. So we like that. Okay? It's pretty efficient computationally. You're not doing a lot of wasted work. Okay? You're not computing very many things that you're not going to use. And this incremental computation is very powerful. You go to a lot of effort to figure out the values at the corners and at the endpoints so that when you're doing a big span, you have very little work to do per pixel. It's just one addition per pixel, and that's really good if you like that. So it ends up being fairly good for large triangles. The bad thing is it has kind of complex control in general, especially when you have to deal with the change in direction here. Okay, so that's a little bit of a pain to do. And there's a lot of overhead when you do small triangles. Okay, so the reason is because there's a fair amount of setup information so that you can make big spans efficient. If you don't have any big spans, then you're not really getting back that cost. So this works really well for big triangles. As triangles get smaller, it's not such a smart thing to be able to do. Any questions about the way this works?
Setup just refers to when you walk along the edge of the triangle?
Okay, so there is setup. In this case, there is setup per triangle to figure out all these derivatives. Okay, there is also setup in this algorithm per span, because you have to figure out what the starting point is and what the derivatives are. Okay, so that's what I refer to as setup. Okay, a cost that is independent of the number of fragments you actually visit.
When you get to like the scope of the triangle, is there anything special being done in parallel, or is it just each process gets a triangle to do, and we'll do that triangle separately?
So this is something that's done. Okay, if you do it in hardware, then I mean, this is very secret, right? So nobody really knows exactly what's happening. If I'm building it, then probably I have a stream of triangles coming in, and I try to have a stream of fragments going out. So if I have a lot of small triangles, then I'm going to need to churn through triangles pretty quickly and do all the setup. If I have a bunch of, okay, let's go back to another case. Let's say I have a whole bunch of really big triangles. Okay, so I have a whole bunch of really big triangles. They're going to flow in, and I'm going to have a triangle, and I'm going to turn the crank and walk through spans and walk through fragments and spew out a bunch of pixels. Now, the question is, can you spew out more than one fragment per step? Okay, and you can if you want to use a little bit of parallelism. You can say, well, instead of hopping every clock cycle to a different fragment location, I can do 2 per clock cycle and hop 2 at a time. Okay. I could do 2 scan lines at the same time and have 4 at a time. Okay, spit out these 4, spit out these 4, spit out these 4. It's a little bit of inefficiency related to that when you get to really small triangles, but in general, it parallelizes fairly well. Okay, so let's say I have a bunch of little tiny triangles. Okay, if I have a bunch of little tiny triangles, then I might not be very efficient in my rasterizer because I have to bring in a little tiny triangle, do all this setup kind of work for it, and then start turning the crank and putting out a pixel stamp, 1 or 2 or 4 pixels every fragment. Okay? So maybe it's going to take me several clock cycles to do all my setup, and that might mean I'm slow. But if I'm doing a whole bunch of little tiny triangles, it's likely that my rasterizer is probably not my slowest part anyway. It's probably bound by vertex performance, not by rasterization performance. So maybe it's not such an issue.
So this is where a programmable rasterizer would be nice.
So if you have a programmable rasterizer and you have a bunch of little tiny triangles, maybe you say, I'll pick a different rasterization algorithm. I'll pick one where setup costs are minimal because I'm spending so much on setup. Maybe then I'm going to go to a bounding box rasterizer. Okay? Because a bounding box rasterizer has almost no setup, right? It's real easy to traverse a bounding box. I don't have to, and so that's where you might benefit from having something programmable. Okay? That's an interesting project to think about, right? Depending on the size of the triangle, what is the most efficient rasterizer in terms of the number of operations? Right? That'd be pretty cool to figure out. And that's something somebody like Intel is going to be very, very interested in because they get to build a programmable rasterizer. Okay, so that's our Scanline algorithm, right? So there's some good things and some bad things about it. This is pretty much what got implemented in early SGI hardware. This is sort of the first rasterizers people built. Now, my understanding is the way that people are doing rasterization now is uses more of this Barycentric formulation. There's some nice things about the Barycentric formulation. And so I'll sort of show how it works, and we'll talk about why it's kind of cool. Okay, so the Barycentric formulation is saying remember that we have a fraction for each one of these each one gets a coefficient that is a fraction of the total area, right? So if each one of these takes a third of the area of the triangle, then each one of these has a fraction of a third, okay? If this whole picture is almost all red because the point is over here, then the red fraction is going to be very close to 1 and the other 2 is going to be small. That fraction is B. So there's B for each one of these triangles, okay? So it's the area of the colored triangle over the area of all the triangles. Okay. So then what we're going to define is our interpolant value is equal to basically the dot product of the weights of these 3 triangles with the interpolant vector, the 3 interpolants, right? So, and this makes sense, okay? Let's say this thing was almost all red, okay? Then the red fraction is very close to 1, and we multiply the red fraction times the value here, okay? Because the value of this interpolant should be very close to the point here. So that makes sense. Okay, it's the right thing to do. And this is a linear relationship. Okay, so this is also linear interpolation. You can get the exact same answers here as if you do the Scanline algorithm. Okay, it's going to interpolate in exactly the same way. The math is just factored in a different way. Okay, so what we need to make this work is we need to figure out what the area of this triangle is as a function of x and y. Okay, that's the tricky part. So if I say I'm at x, y here, what are these 3 areas as a function of x and y? That's what we need to be able to make this work. Because then if we have those areas, we can easily calculate these fractions, and then we can very easily calculate the interpolant value. Okay, so what is this area as a function of x and y? So we know that the area of a triangle, okay, is equal to half of the cross product of the 2 vectors that make up the triangle. Right? So if you take the cross product of this, it will make a parallelogram. Okay? And the area of that parallelogram is equal to the magnitude of the z component of that cross product, and then we divide it by 2 because we're on a triangle and not a parallelogram. Okay? So then we can calculate this whole guy out. What is a as a function here? We multiply the whole thing out. Okay? So just do our math here. Okay? And we come out with this expression. The area of the red triangle is equal to a constant value times x plus a constant value times y plus a constant value. So it's a very simple expression. It's a very simple expression to be able to get the area of this particular triangle. Okay, we need to calculate a, which we already did when we did culling, and then 3 different values, the areas of the 3 colored triangles. One for red, one for green, one for blue. Okay? But it's really simple to be able to do this. Okay? What if this area is negative? What does that mean? Okay, don't rasterize. Well, I mean, don't bother, right? It's outside the triangle, so we don't really need it. We know this is going to be positive. Or if all three of these areas are positive, we know we want to keep it. Right? So again, this is another algorithm that nicely combines traversal, okay, telling if you're in or out of the triangle, with parameter interpolation. Okay, so we come back to this picture. We know that we wanted the area as a function of x and y, and it turns out the area is a very simple function of x and y. Okay, big thumbs up there. It means that we can calculate areas linearly. Okay, so we like that. Okay, we like that a lot. Because if we calculate them linearly, then as we walk across a scan line here, okay, the difference in the red area here versus here is just the difference in x being here and x being here. So it's just a difference of 1 between x, right? So the difference in the area here versus here as we perhaps walk across a scan line is just alpha 0, right? Alpha 0 of x is 12 versus alpha 0 of x is 13. Okay, it's just an incremental calculation, just like we saw in the scanline calculation. So that's kind of cool. So the setup costs that we have here, okay, the setup costs that we have to do, well, what are the setup costs? We're looking here, what are the setup costs? The costs that don't matter on the size of the triangle. What do we have to calculate for every triangle? Okay, we have to calculate this area here, okay, which we did in Colleen, which is good. What else do we have to calculate?
We have to calculate I0, I1, I2.
Well, this is a function of x and y, so no.
Okay.
Okay, but what can we calculate per triangle? Only once. Okay, if we go back here, what can we calculate per triangle?
Gamma?
Yeah, gamma. What else?
Alpha, beta?
Alpha and beta. Okay, so we can calculate alpha, beta, and gamma per triangle. Okay, so that's setup cost. And we have to do this 3 times. We have to do it for A0, A1, and A2 for the red, green, and blue triangle. Okay, so basically we have to calculate 10 things here. One is the area of the triangle. And then we have to calculate 9 coefficients. Okay, alpha 0, alpha 1, alpha 2. Beta 0, beta 1, beta 2, gamma 0, gamma 1, gamma 2. Okay, so then per fragment, okay, as we're walking along the triangle, okay, whether it's the Scanline algorithm or one of the twisty ones or whatever, as we're walking this and figuring out which ones are in the triangle, all we have to do to figure out what alpha 0 is, if we know a current alpha 0 and we hop 1, is we just add an alpha 0 or add a beta 0. Okay, as we move plus 1 or minus 1 or plus 1 up or minus 1 down. So it's very simple to, if we have one point of alpha 0, to get the neighboring point alpha 0. Or sorry, A0, not alpha 0. So that's kind of cool. So work per triangle. So just to compare these two, okay, Scanline, you have to do setup costs, you have to do the edge equations, and that's going to require we do 1 divide per edge. Okay. The other thing you have to do is you have to sort the triangle. Okay. It turns out this is really important. If you have this triangle here, you always have to render it in the same way. Meaning, if I'm rendering this triangle and I'm sort of walking up this edge here and picking out the values, okay, and I'm going from bottom to top, and then I take the next triangle that's next to it, and I render it by going top to bottom. Okay? So we figured out what this initial value is, and then as we're walking up here, we're using these deltas that we calculated and getting all these here. If we then render this triangle, but we start top to bottom, and we walk it this way, theoretically those two things should give you the same points. Okay? In practice, they don't, and it's because of floating point and precision. Floating point is not perfectly precise. And if you rasterize that way, okay, if you rasterize this guy in one direction and this guy in a different direction, okay, then you're going to get the wrong answers. You're going to end up with some holes or some double counted points or something like that. The story is if you build a rasterizer, you have to make sure that the traversal of any given edge happens the same way. Okay, so what I'm describing here is a way that you start with the smallest y and you always rasterize bottom to top. Or you can make your rule that you always advertise top to bottom. As long as you make a rule that the traversal always, always, always happens in the same direction. If you don't, then bad things will happen and you get hold. And I know this because when I built a rasterizer for my dissertation, that's exactly what I found out. Okay, so you have to be able to put the triangle in some sort of canonical order so that when you traverse it, it's always going to be the same. Okay, so this is the work you have to do for the Scanline algorithm. For the Barycentric algorithm, you have to calculate all these coefficients. Okay, then how much work do you have to do per fragment? Both of these end up being incremental evaluation, which is really the advantage of these two techniques. That as you're walking through the triangle, if you want to go from one pixel to the next pixel, that's just usually an add per interpolant. So that's kind of groovy. Okay. If we want to do more than one fragment, if we want to get some parallelism, then the algorithm here is Juan Pineda. And this was done a long time ago in SIGGRAPH 1988. But he sort of showed that, well, exactly what I explained a little earlier. Instead of just doing one per hop, you sort of stamp out an entire pixel, a stamp at a time. So instead of just doing one fragment with every clock cycle, you can do several. Okay? So the deltas just end up being linear. Instead of hopping by one delta, you hop by two deltas, and it ends up working. So, and then you mask this out using the edge equations if you need to. So the vendors don't really tell you so much about exactly how much stamping they do or how much they do this. I did find this one slide from, and this is old, 2001, but the GeForce sort of how they're actually doing it. Okay? So what they're saying is in this particular chip, they had a stamp that was 2 by 2. Okay? So every cycle they're stamping out 4 pixels, unless they're doing a lot of work. So if you're doing a lot of multi-texturing in this particular thing and you're doing a lot more work per fragment, then maybe they cut it down a little bit. Okay? But it's pretty clear that they do this. Now, what's the disadvantage of doing pixel blocks? Why don't we go to 4 by 4 pixel blocks or 8 by 8? Okay? We have the hardware.
Wouldn't work very well for small triangles.
Okay, it would be inefficient for small triangles, right? So we end up doing this nice 8 by 8 or 4 by 4 block here, and we've got all these points, and then we have this little tiny triangle that covers one of those points. Okay, it's a big waste of time to try to rasterize 16 things at a time if only one of them is going to hit. So the smaller the triangles are getting, the more inefficient it is to do parallel rasterization work. Okay, now it might be that we have so many transistors now it doesn't really matter. Okay, because if you have big triangles, it totally rocks. It's really good. Okay, yeah.
So why isn't it possible to have a variable size that, depending on the frame, you can just change it how you need?
Well, I mean, if you're building a hardware rasterizer, the issue is that if you're paying all this money to design it in silicon so that it can stamp out 2 by 2 blocks every frame, well, then does it really make any sense to turn off some of that?
Well, if it makes it better for smaller triangles, you can have like a 16 by 16 and size it down for different.
Okay,
size
but
triangles.
in hardware, if you've already paid for a 4 by 4 one, okay,
that's true.
You've already paid for it. You might as well use it. So it's going to be inefficient, but you've already paid for it. Now, from a power perspective, it might be possible to, cut it down, and maybe you can turn off some of it. But it's hard on a chip to turn off little pieces of things. You can usually turn off big units of things, but it's hard to turn off just a few transistors at a time. Okay, but that's exactly why a software rasterizer might make sense. Okay, now you look at this sort of thing, and I mean, there's a fair amount of math per triangle. So this is roughly on the order of 50 or 100 ops to be able to completely set up a triangle and calculate all this stuff. So that's a fair amount of work. Okay, and it's very parallel. It's something you can build very efficiently in special purpose hardware. Okay, which is good. So anybody that's starting with a programmable rasterizer has that big gap to be able to fill. Okay, how quickly can you set up a triangle when a custom rasterizer can do it in one cycle? Okay, but once you do that, maybe you can get some better efficiencies by being able to deal with small and large triangles. And so this will be a good thing to ask the Larrabee guys when they come visit. How do you really do this? So one of the nice things that they appear to have done is they have they have an instruction set that they have designed to do rasterization efficiently. Okay? So when they have their programmable rasterizer, they basically have instructions that look like edge equations. Right? You throw in a point and a line, and it can do that in a single cycle. say which side of the line that point is on. Okay? They haven't released any details about this sort of thing yet, but that's generally understood that that's what they've done with it. So they've really specialized their instruction sets so they can do rasterization very efficiently in software.
If you want people to use something like Larrabee so that they can program their own rasterizer, don't you have to reveal more about your hardware to let the programmers know how to program it efficiently?
Sure, and Intel's usually pretty good about that, right? So Intel as a company historically, it tells you lots of things about their hardware. You can go buy an Intel programming manual for the, Pentium 4, Core 2 Duo, and they will tell you everything you need to know. You'll know exactly how the pipeline is built. You'll know what all the weird interlocks are. They'll tell you this stuff, and they'll give you a big book. It's not something NVIDIA does.
So they're doing a very different approach than like the other graphics companies than, say, ATI or NVIDIA.
They're taking a CPU. Well, I don't know about Larrabee. I mean, it hasn't even launched yet. Their CPU, in the CPU world, though, people are very open about the way their chips work because you need that to write things efficiently. GPU vendors are not nearly as transparent. I expect Intel will probably be more of a CPU take. And you need to. I mean, you have to because otherwise, people won't know how to program that thing efficiently. Okay. Any questions about parameter interpolation? Okay. So now we're going to throw in another wrinkle on this. Okay, we're going to say, all right, we just learned all about parameter determination. That makes sense. We can do it with this nice dot product thing. We can do this nice linear interpolation. Okay, linear interpolation is great. It solves all our problems. It makes total sense. Okay, we're going to build this. Take our 3 points, build this one linear plane. Bam, we're done. Okay. Now, it turns out that it's completely untrue in practice and it doesn't work. So I've just taught you sort of the theory of linear interpolation and how it might work, and maybe it makes sense to linear interpolate those things. And that works for colors in general. If you want to linearly interpolate colors, okay, they're going to look fine. Okay, it doesn't work for something like. So I need an eraser now. It doesn't work for something like texture coordinates. So now I'm going to do some derivation on the board to show you why that's the case. Okay, so I brought my notes. Okay, so we're going to start over here, and we're going to pick a particular coordinate. We're going to call it u, which is, say, a texture coordinate. And we're going to say that u is equal to some function of I coordinates. And we're going to say v is a different coordinate, and we're going to say that that's some other function of I coordinates. Okay. Now, when you specify something in world space, okay, out there in some sort of 3D space, and you say that, out in 3D space, this is red, and this is green, and this is blue, okay? In world space, you want that to be interpolated linearly, okay? That makes sense that it's interpolated linearly, okay? You want it to be linearly interpolated. What I'm going to demonstrate, though, is that when you take this thing out in world space, and then you put it into screen space, okay, that if you interpolated it linearly here, you can't linearly interpolate it here. Okay? Once you go through all these transformations, okay, linear interpolation out here is not linear interpolation out here. Okay, and I'll show you that that's the case mathematically, and then we'll look at some examples. In fact, I'll just do that right now. Okay? We've got these points here, out there in world space. Okay? We've got these lines. Okay, we got this line, and this works for triangles too. Okay? And we specify this thing as being linearly interpolated, and we say, here's a line, here's P1 and P2, okay, out in world space. We look at P, okay? So if this is red and this is blue, should this be linearly between red and blue? Okay, it's pretty much halfway in between. It would make sense. So you specify this line, you say, I want to draw it, I want to interpolate between these two things, that would make some sense. How about Q? Is Q halfway between Q1 and Q2? Probably not. So you wouldn't want that value to be halfway between. Okay? So we want to specify our points in this way. All right. So then what we do is we put in a camera and we do a projection. Okay? And now we see how these things project on the screen. And we say, is P now halfway between P1 and P2? Okay? No. Is Q halfway between Q1 and Q2? Yeah. Okay, so that's sort of backwards from what we expected. Okay, the big picture, and I'll now show this mathematically, is that linear interpolation in world space is not necessarily linear interpolation in screen space, and vice versa. Okay, and it's because of this perspective projection. Okay, the perspective projection is obviously a good thing to be able to have because you can do good effects with it and it makes things look correct, but you can't do linear interpolation anymore. So what I'm going to show you is how you do interpolation that's going to end up having the right effect. The right effect is that you want to do interpolation in world space. Okay, you want to have the effect of the interpolation in world space. But all we can do is interpolate in screen space. How do we interpolate in screen space and still get the correct effect in world space? So I'm going to show how that works. Okay, so I'm saying that U and V are things we want to interpolate, and the right thing to do is do it in I space or some sort of world space. Okay, that's where we want to actually interpolate things. So this is called an affine mapping. Okay, we talked about affine stuff. And so I'm going to express this as a little matrix here. Okay, some sort of 3 by 3 matrix we're going to call T. Okay, times x sub e, y sub e 1. And it's going to be equal to T times x sub e, y sub e 1. Okay, everybody cool? So I've just taken these two things, I've combined them here. Okay, and you're going to say, ooh, why do you have that 1? The 1 comes in later. Okay, so now what we've mapped here is U and V as a function of x sub e, y sub e. Okay, done with that. Okay, so now what we want is U. Okay, so what we want, so this is what we have. What we want is U and V as a function of x of s and y of s. Okay, and possibly w of s. Okay, we want to figure out what U and V are in screen space. Okay, we know how they interpolate here in I space. How do they interpolate in screen space? Okay, that's what we're going to try to figure out. So what we're going to figure out is how we get x sub e and y sub e as some sort of function of screen space coordinates. Okay, so then I can combine this and this to give me this. Okay, cool. So now we're going to say that the screen space coordinates xs, y, s, w, s is some sort of 3 by 3 matrix here, this projection matrix, and I've left out z coordinates everywhere just to make things a little bit simpler, of x sub e, y sub e 1. Okay? Right? So the way we get from world coordinates into screen coordinates is the perspective projection. Cool? Okay? So we can switch these things around. We can say x sub e, y sub e, w sub, 1 is equal to P inverse times x sub s, y sub s, w sub s. Okay? So now we have what we actually want here. We can say U and V and 1 is equal to T times P inverse times x sub s, y sub s, w sub s, which is equal to some sort of matrix which is equal to this, x sub s, y sub s, w sub s. Okay, this is great. Now we got U and V as a function of screen space coordinates. Okay, we're happy with that. Okay. Now, remember, cool, let me make sure I got this straight here. Okay, so we want this, but what we really want is U and V as a function of x and y. Right? These are the homogeneous coordinates in screen space, but what we really, really want is U and V as a function of x and y, which is actual screen space coordinates. Okay, so how are we going to be able to do that? Okay, so now we can look at this guy and we can say U is equal to AXS plus BYS plus CWS. Okay, if I multiply out this M matrix here, okay, we've got this. So this is a nice linear relationship here. Okay, but what we need is x and y, not x of s and ws. Okay? Remember how homogeneous coordinates work. We know that x is equal to s of s over w sub s, and y is equal to y sub s over w sub s. Okay, we do the homogeneous divide there. So we're going to divide this whole thing by w sub s. And that's going to give us u over w sub s equals a xs over ws plus b ys over ws plus c, which is also equal to ax plus by plus c. Okay, now we want this. Okay, u and v is a function of x and y. What we actually got here is u over ws as a function of x and y. Okay, so u is not a linear function of x and y. Okay, we know that here, right? These are not linearly interpolated. Okay, u is not a function of u is not a function of x and y, not a linear function of x and y. But u over w is a linear function of x and y. Okay, so that's really good. All right. Now, the problem is, how do I get from u over w sub s to u? And so it turns out, if you look at the last line of this matrix, if we multiply this through, we get 1 equals, we're going to call it, for the purposes here, gx, I'm sure that's right, x sub s plus h y sub s plus I, right? So I've just multiplied the last line of this matrix here. And if we divide that through, REWS, if we divide the whole thing through by WS, what we get is 1 over WS equals GX plus HY plus I. So these are really our two equations here. Okay? We can't linear interpolate u. Okay? It doesn't work. You see it on the picture there. We can linearly interpolate u over w, and we can linearly interpolate 1 over w. Okay? So if we do linear interpolation here, and we do linear interpolation here, we're done, because we linear interpolate this weird thing and this weird thing, and then we can say u is equal to u over ws over 1 over ws. Okay. So that's good. So let me repeat this. Don't have to worry about the math so much, but the big picture is, if you want to do linear interpolation with texture coordinates, okay, it is not cool to linear interpolate the texture coordinate directly. Instead, you linearly interpolate the texture coordinate over w, you linearly interpolate 1 over w, and then you divide this by this, and you get u, back what you want. So what this means in practice is, nobody linear interpolates any coordinates, okay, any interpolants at all. You don't linearly interpolate red, green, and blue, and depth, and texture coordinates, and normals, and so on. What you linearly interpolate is the interpolant over w. Okay? So if you have k different things to linearly interpolate, you interpolate all of them over w, and then you do one additional interpolation. And there you interpolate 1 over w. Okay? Then you do all your math all the way through. Okay? You do all your interpolation with whatever method that you choose to do. It's one extra coordinate here. Then, at every pixel, you have to figure out this value. Okay? So you would normally have to divide this by this, but in practice what they do is, on every pixel, you take 1 over ws, you get u over ws times ws, and so for every interpolant at every pixel, you multiply ws times what you actually interpolated and you're done. What that means in practice is, to get this, the reciprocal of this, to get ws back, requires that you do a divide at every pixel. Okay? So every pixel you do your interpolation, you have to figure out what ws is. You've interpolated 1 over ws the whole time. Okay? Then you get to 1 over, so you take 1 over that. So that applies to all the different interpolants you're going to do, but it does require, to do linear perspective correct interpolation, you must do a reciprocal at every pixel. Okay. That is why there wasn't texture mapping in any sort of hardware until, the first texture mapping came in like 1994, 1995. It's because it was way too expensive to do divide at every pixel. Okay. Big, big, big picture. To do perspective correct interpolation, you have to do this divided every pixel to make sure that things are going to be perspective correct. Okay. If you don't do this, what happens? Okay. If you don't do this, you get perspective that looks like this. Let's say I'm doing like a window-looking thing, right? If you look here, this might have been a window that's nice and, quarter, quarter, quarter everywhere. Okay? But if you do it in correct perspective here, then this is going to be different than this. Okay? You're not linearly interpolating in screen space. Okay? That would be bad. Instead, you have to linearly interpolate in eye space and translate your results over. That's what this math tells you. Okay? Otherwise, you get something that looks bad like this. Right? This is incorrect, and you would know that it's incorrect. It's because we linearly interpolated in screen space. What it means in practice you're going to get is you're going to do like a checkerboard here and a checkerboard here, and you're going to see these two things don't line up. Right? This and this triangle are both linearly interpolated, and notice it doesn't really look like a very good checkerboard. So if you ever build your own rasterizer and you don't do linear correction, you're going to get weird seaming artifacts between your different polygons. It'll look okay for just one polygon, not perfect, but okay, but it isn't going to match up nicely with other ones. Okay, so can't interpolate U and V. We can interpolate U over W and 1 over W. So this is what we actually interpolate, and we have to do this in setup. Okay? Or we do it at the end of the vertex program. Okay? We have to do an extra divide per vertex for every setup and a divide per pixel at rasterization. So we should do it on these things. It's the right thing to do it on those things. You can get away with not doing it sometimes. Okay? RGB, if you don't do it, you're not really going to notice. Okay? It's just color interpolation. But for texture coordinates, absolutely you will notice it. Okay, so what you get if you don't do it right is swimmy sort of artifacts that look like this. Okay? This is very clearly wrong, and it kind of makes your eyes look a little bit funny. What you can, basically, the function, the interpolation function, actually looks like this. Okay? If you do it wrong and you linearly interpolate and you approximate this with a line, then you get something that looks like this. What you could do is be able to take pieces out of this, sort of piecewise linear interpolate it, and make it look a little bit better. And that's what we've done over here. In practice, nobody does that anymore. They actually just do the divide on every pixel. Okay. So if we want to do this in the Scanline rasterizer, or we want to do this in the Barycentric rasterizer, how do we do this? So for either one of these things, we have to keep track of this additional interpolant now 1 over W. All right? So the Scanline rasterizer, every time we get to a pixel, we have to take 1 over W, so we get W back, and multiply it by the interpolant over W and get back our interpolant value. Right? So this is the extra divide we have to do at every pixel. For the Barycentric rasterizer, it's a little bit different. It used to be that we took this fraction and just took the value of our triangle over the value of all the triangles. Okay? Now it turns out that that's a little bit more complicated. The math gets a little bit worse. So, but it's really not an enormous amount more work. Okay? The nice part here is, we're going to talk about this when we get to, with the Barycentric rasterizer, that we need derivatives of these functions also. Okay, so we've got these functions. We'd like to have the derivatives of these, and they're very useful when you're doing texture mapping. And we're going to see that probably not today, but probably a week from today. Why derivatives are good. It turns out this method is very well suited for derivatives. And so I'm just saying we can get derivatives out of this particular process. Okay, so any more questions about this linear interpolation thing? I know it's a little bit mind-blowing. I know the math isn't all this much fun, but it's important to note if we do this, we can't linearly interpolate and get correct results. Okay, we have to do these extra steps. Okay, now, yeah?
Just conceptually on WS, is that like the, like almost the slope of the line from world space to?
We're actually going to see what that is in the next example, so I'm really glad you brought it up. Okay, so this is just the homogeneous coordinates, XS, WS, and YS in screen space. So, you have to divide those out eventually. Okay, so we're going to see what W sort of means here. Okay, and what if W was constant across a scan line? Okay, so that's the question we want to ask. Okay, what we've seen is, let's say we're doing this triangle here, okay, and we're going across a scan line here. what we would normally have to do is figure out what 1 over W was here, and 1 over W was here. Okay, 1 over W0, 1 over W1, and then we sort of do the incremental thing as we walk across here. Okay, so what if W was constant across a scan line? Okay, how does that help us? Okay, so we're going to look at this perspective transformation over here. Okay, what does the math actually look like? What does it mean if W is constant across? So this is the projection matrix to do a perspective transformation. Okay, and this is what this actually looks like. So you don't have to worry about what A, B, C, and D are, but this is what the matrix actually looks like. If you do man-geo perspective, you're going to get this. We're going to multiply this times I coordinates. Okay, and so that's going to give us the following. That this is going to give us screen coordinates. Okay, BYE ZS equals ZE plus D. Okay, I hope I did all that right. So I just multiplied this whole thing out to get the perspective transformation will give us the S coordinates here. Okay? And this one's pretty important. We're saying, okay, in here we're saying we have a triangle. Okay? We would love it if it had the same 1 over W at both places. Okay? Because then you don't have to go to all this effort of dividing it through. Okay, we don't have to divide it every pixel. Instead, we only have to divide once per scan line, right? We just do 1 over W here, and it's the same all the way across here. Okay, there's a good punchline to all this. Okay, so if W was constant across a scan line, we have a lot less work to do because we only do 1 reciprocal per scan line instead of 1 reciprocal per pixel. Okay, when is W constant across a pixel? Sorry, across the scan line. When is W across the scan line according to this?
The triangle is parallel to the viewing point.
Okay, so I mean specifically we have X, Y, and Z. What criterion is it?
When the depth doesn't change across the triangle.
Okay, so if we have a scan line where the distance from the camera is the same across the whole scan line, then our life is much easier. Okay, say that again because it's important. Okay, we're rasterizing here. We have some weird scan line that looks like this. This is our triangle. Okay, we have to go to the 1 over W at every pixel. If we have constant depth away from the camera at a scan line, okay, we can build a much more efficient rasterizer. And I bring this up only because this is the particular thing that allowed us to build Doom. Okay, this particular realization that if we have a triangle here, okay, and the triangle has constant depth across a scan line, then we can build a much more efficient rasterizer. Okay? 1994, when Doom came out, you didn't have enough compute to be able to do a divide at every pixel. Okay? We have huge triangles here, though. And in a huge triangle, okay, we go across here, and if you look at any Doom floor, okay, this line right here is a constant distance away from the camera. Okay? This line right here. Okay? In Doom, you can't turn your head. You can't turn your head because you need to keep that characteristic so that they could be able to run this in real time. This was the most important thing they needed to do. They could not afford to do a triangle per pixel. They could not afford to do a divide per pixel. They had to have it so that every scan line only took 1 divide, and that made it possible for them to be able to do it. Okay? So if you look at this surface or this surface here, every triangle they do is the same distance away from the camera. Okay, so how about here? Look at this line. Is this the same distance away from the camera? Okay. No, so how'd they do that? Because this was really clever, too. Okay, they really need scan lines that are a constant depth away from the camera. If they do that, they can build it more efficiently.
But in this part, it's the same.
So when you get to do wall polygons, you make your scan lines vertical. Because any vertical stripe here is a constant distance away from the camera. Very nice. Okay, so all floors are rasterized this way, all ceilings are rasterized this way, any walls can be rasterized vertically.
So I'm still trying to figure out why can't you turn your head? Like you're saying you can't tilt your head this way?
If you tilt your head, then if you scan this way, things
Yeah.
are going to be different. Okay, they're not going to be the same distance around because the whole scene is going to sort of tip, right?
Oh, I see, yeah. Okay.
Okay, you could do that in future games when they got the texture, when they got enough hardware where they could afford to do a divide on every pixel.
So you could tilt your head, but you'd have to use diagonals instead of just horizontal or verticals.
It's not practical
Kind
to
of.
be able to rasterize diagonally.
Yeah, yeah.
Everybody will rasterize either horizontally or vertically. But there's nothing tying you to doing it horizontally, and so it's very nice to think that you could do vertical scan lines. In fact, it makes more sense from an efficiency point of view if you rasterize in whatever direction is going to give you fewer scan lines because there's some work you have to do on every scan line. So you have a triangle that looks like this, you want to rasterize this way rather than this way. Okay, so there's a lot of restrictions in Doom that basically come down to this particular thing. Okay, can't turn your head. The geometry's all done in a certain way so that they could do their tree. I mean, there's all the things where you say it sucks you can't do this have very good reasons in graphics. Okay, but this is the cool one right here. Okay, cool. Last thing I'll show in this lecture is some slides from Kurt Akeley on how people actually built rasterizers in SGL hardware. So what did they propose to do? So this is starting from some of the earliest hardware all the way down to some more recent sort of stuff. So the things you want to think about when you're building a rasterizer is what's the setup cost and what's the execution cost. So setup cost is per triangle, execution cost is per fragment. Okay, how well can you parallelize? Okay, that's important. And how well can you cull? Right? How easy is it to say, I can throw out this whole triangle because I'm culling only to a special region? And so OpenGL has a particular command called scissoring, and you can set up a scissor region, which says I'm only rasterizing in this little part here. Okay? And you want to be able to do that efficiently. Okay? You want to be able to support pulling out of a particular, where you're only going to draw things within a certain screen region. So GTX ended up being really the very classic scanline kind of algorithm here. Okay, so you sort of walked along edges. DDA is this differential something analyzer. Okay, and then you picked out your fragments. Basically, it's exactly the same one that I talked about. And then you walked along a scan line here. Okay, so the setup cost per scan line ends up being fairly high because once you get to the right scan line here, then you have to jump a little bit to get to the next vertical scan line because you always have to start on like an integer boundary there. So that little bit of math ends up being a little bit complicated there. Not good at scissoring, but did work on quadrilaterals. Okay, we'll talk about this later in the class. But this is a machine from North Carolina called Pixel Planes. So this was kind of cool. They built a processor at every single pixel. Okay? Every pixel in the machine had its own processor. Okay? And every pixel would every time a triangle would come in, every pixel would see that triangle. Okay? And it would all say, okay, am I in this triangle or not? So every pixel would solve the edge equations. And then what's my parameter? Okay, so do my parameter thing. Right? It's great. Right? Isn't that cool? Processor at every single pixel there. Okay, that's really, really cool. Setup, you would need to figure out all the slopes, and the slopes would allow you to figure out what the coefficients were to be able to do these. You would broadcast to all the pixels there. So that's pretty cool. So what's this really good for, and what's it really bad for? Okay, this seems kind of cool, right? Okay, why would this be less efficient for certain things?
So I think if you had like scenes where there's a lot of overlapping stuff, it would make sense because then each pixel is able to work on a multiple number of triangles and find out. Well, not work on it, but But if there's small triangles or something like that, then a lot of the pixels are just sitting around waiting.
Okay.
And doing nothing.
So that's sort of the Achilles heel of this. This is really nice if you have giant triangles. Okay, you got giant triangles, you throw it in, every single pixel is going to look at that triangle. Okay? So if you have a triangle that takes up half the screen, you're getting all those pixels computed in parallel, which is great. Okay? Then I send in a little tiny triangle, and you've got 1,000,000 pixels, and it covers 2 pixels. Then the other 999,998 pixels are wasting their time because they don't cover that triangle. So this was a really nice architecture for big triangles. Okay? It was not a nice triangle for small triangles. Okay, that didn't work out. Okay, but it was a really cool way to think about doing this. And so the engine at every pixel ended up being very, very, very simple. All it could do was ax plus by plus c. But that was enough to do parameter interpolation. And it was enough to calculate the edge equations. Right? So it's just a little tiny processor, but there was one at every pixel. Okay. So then they moved to the next chip. They did, this is a particular edge walk algorithm they had here. And it was sort of a hybrid algorithm between walking the edges of the triangle and walking parameters inside the triangle. So to figure out which fragments you hit, you use the edge walk. To do parameter assignment, then you stayed within the triangle and you sort of just walked from pixel center to pixel center. Okay? So you never had this problem of figuring out how to do this little gap right there. Okay? You only had to pop onto a pixel center once. So that was really good. So that worked out fairly well. There were some tricky bits of it. So when we look at this thing, okay, let's say you're building interpolation hardware. All right? And you have red, green, blue here. Okay? And you know that red, green, blue range from 0 to 1 in floating point coordinates. Okay? So, do you ever, when you build your circuitry, okay, your internal walking circuitry, and you're calculating red, green, blue as you're walking here, do you ever have to have a value that's outside of 0 to 1? Okay? So in theory, no, because you never leave the triangle. So you build something where your internal representation of the color there is always exactly from 0 to 1. Make sense? Okay, so the problem is you don't actually get to be able to do that. And the problem is when you have like skinny kind of triangles like this, and you're only hitting this pixel and this pixel and this pixel here, okay, the problem is if you're doing this walk, you have to go outside of 0 to 1. Right? You don't have any choice. And you can make it arbitrarily bad if you have a really, really skinny triangle. So that's an issue. And so that made things a little bit more difficult to implement. Okay. When they moved to infinite reality, which is a machine that came out in 1996, they moved to a more hybrid algorithm. This used sort of edge walk in the same way the other ones were to do fragment selection. This was the first one to do Barycentric evaluation, to do parameter stuff. So that was kind of cool. This ended up being a better thing for them to do small triangles. It took less setup than the Scanline approach, which is pretty good. This was also the first one that did guard band clipping. What they proposed in Bali, so this was the machine that was going to come after the infinite reality. They named it Bali because they were expecting to get a trip to Bali when they finished the machine. So pretty ballsy on their part. Unfortunately, they never built the machine. So SGI sort of went into hard financial times. So this machine never got built. But this is what they proposed to do, that they were going to do tiled rasterization. So they tile the whole frame buffer into tiles and then rasterize at the tile level and the fragment level. So this is sort of, well, we looked at that in one of the first slides today. So this ends up being a very efficient thing. This sort of two-stage, this two-level algorithm is what GPUs do today as well. Okay. What Kurt felt like was the issue here with new NVIDIA hardware was this algorithm called homogeneous recursive descent. So clipping is, as we learned in the geometry phrase, a little bit difficult to implement. And so what he felt NVIDIA was doing at the time was not doing clipping in the geometry stage at all. They actually did homogeneous rasterization. So they didn't rasterize with X and Y and Z. They rasterized with X sub S and Y sub S and W sub S. So it was 4-dimensional rasterization, or 4 vectors instead of 3 vectors. And so there's some really nice theoretical ways to do this. So Alano and Greer go through all the math to be able to do it. It's very hard to understand. I read it several times, and it's really, really tough. But it's kind of cool. And so they rasterized in homogeneous space as opposed to converting into screen space. Then they never had to do the perspective divide, which was kind of cool. So this recursive descent was you start with big tiles and then you go down steps to make smaller and smaller tiles. So it's pretty handy. Eventually it gets down to 2x2 stamps. What I think people are pretty much doing today is they rasterize in like 8x8 style tiles. So that's the size of a tile. They go straight from triangles to these sort of tiles and then rasterize within that. So it's sort of a two-step process. But again, this is the sort of thing they really don't like talking about very much. So it's hard to know exactly what they do.
You generate like pixel masks while you're walking the triangle?
So
like coverage masks, I mean.
You probably have enough parallel hardware where you don't. So you rasterize two tiles and you figure out which tiles are alive, and then within that you just go through the stamp on it. So I don't think you necessarily generate a coverage map. You just stamp and then you evaluate the equations at each fragment. That's my guess.
Okay. I guess for aliasing, I'm thinking.
Well, we haven't got to multi-sampling yet.
Right.
So that'll come in 2 lectures. But we will talk about that. Okay. Right now we're only worrying about taking 1 sample per fragment. That is not going to be the case in 2 lectures. Okay. But all the same rasterization stuff still applies. Okay. That's all I got for rasterization. I'd like to start some texturing. But first, do we have any questions on rasterization? All right. So I'll just do sort of an intro to texturing. And then we'll do most of this next Tuesday. Okay, so I just want to talk about textures at a high level here. Okay, so the way OpenGL does it is that they associate textures with geometry. Okay, when you say this texture is associated with is geometry, you say, okay, this triangle is bound to this particular texture or this set of textures. And so what you do is you associate texture addresses with every vertex. Okay, and then the rasterizer will interpolate those texture addresses across the triangle. This needs to be done perspective correct, or else you're going to have some crazy artifact. Then we have a texture address at every fragment, okay, that's going to resolve to an address within the texture, a region within the texture, a point within the texture, and we're going to see this in more detail. Okay. Then you go look up in that texture, in this image, the particular color you want. Okay. So you have a texture address, you bring back a texel color. Okay? And then you combine that with the rest of the colors or other textures or something in a fragment program, and that's going to give you an eventual final color. This is the way we actually use it. So it's nice to use textures because it saves us a lot of complexity. Right? If we have this very complicated picture, it's just a picture. Right? It can be easily modeled as a picture, and we can use that instead of specifying tons of geometry. It's a lot easier to do a picture of a brick wall than to actually model a brick wall with lots of nooks and crannies and several different blocks, right? We just do one big triangle, one big rectangle, and we slap a brick wall over it. So that's really good. It's very fast. You can use photographic images, which there isn't any other way to do it, to put an image in rendering. And in general, this sort of global gather where you can give it an address and it'll go out in memory and grab whatever you want is a very powerful general purpose computing technique. Now, there's several kinds of textures. So we can have 1D textures. And so what are these actually used for? It's like 1D texture. That seems pretty silly. Okay, one thing is contour lines. All right, so I set up a texture that looks like this. Okay, and it's black everywhere because it's got white lines that go across here. And I index it in this one-dimensional way here. Then I draw terrain. Okay, and at every spot in the terrain, it looks up its altitude. All right, if it's actually on a contour line, it'll pick up this white value. Otherwise, it'll pick up a dark value. So when you actually look at it, it's going to look like contour lines across a place where it's the same height. So that's kind of cool. You can also do altitude indexed color. Right, it can be white or blue up here where it's cold, and like nice and green and sunny down here. This is also used for the same sort of technique when you're doing a transfer function in visualization. Right? You have a function, you have a value, and you have to get a color for that. Okay, you can do that with a one-dimensional color lookup. It's just a one-dimensional lookup table. If you want to do rain, okay, you have a one-dimensional texture that has some transparent parts and some filled-in parts, and then you just sort of change the address so the rain moves down. Okay, but it makes rain look pretty good. Okay, we're used to doing 2D textures, images. That's pretty easy to explain. We also can do some volumetric textures, and so that's either a volume texture where it's actually 3D, or a time-varying texture where you have sort of a set of 2D images and you walk through it in time. The third dimension is time. Okay, you can put other cool stuff in textures too. This is, in my view, a really cool project. This was done at SIGGRAPH a few years ago. These guys put geometry in textures. All right, so what they did is they took this bunny and they sliced him open, okay, and they sort of stretched him across this 257 by 257 image, Okay, so he's now been skinned, and you take his skin and you put it on a 257 by 257 grid, right? And then you put the position, the original position of whatever point is on the grid on into the texture, right? So every point in here has an x, y, and z coordinate, and it's being expressed here as red, green, and blue. Right? So red, green, and blue in the texture corresponds to x, y, and z. Right? Then you can render it back from that. Okay? So this contains all the information that's in this bunny here. You can do the same thing with a normal. Right? These are the normals. So instead of storing 3 directions, we store those directions as x, y, and z. All right? And so then we can make things look all cool, you know, normal mapping and so on. We can do. So the really cool thing here is now you can take image processing techniques and manipulate these images. So I could take this image and compress it using JPEG compression, right? That would probably look pretty good. I could make it smaller. I could, you know, downsample it where it's 128 by 128. Right? I can do imagey things to this, and really what I'm doing is I'm manipulating the geometry. Okay? So it's a pretty cool thing. People put all sorts of crazy things in textures because it's very powerful to have this gather mechanism where you can just reach out and get whatever you want. To first order, a modern GPU minus the programmable parts is just a giant texture engine. That's all it's really good at. It's good at being able to do lots of parallel reads from global memory and scheduling those very nicely. So people have used textures to do all sorts of cool, crazy things. Anyway, this is one of my favorite projects there. Okay, you know, that's probably all we'll do today. So see you guys on Thursday.